Hello friends, welcome to my lecture on Laplace equation. This is second lecture on Laplace equation. In the previous lecture we had considered a two-dimensional Laplace equation in Cartesian coordinates and polar coordinates, and we did one example on polar coordinates in that lecture. Now in this lecture we begin with another example on Laplace equation in polar coordinates, and then we shall be doing Laplace equation in 3 dimensions, and there we shall be considering Laplace equation in cylindrical polar coordinates. So let us begin with the Laplace equation example on Laplace equation in polar coordinates. Let us take up the case of a circular membrane of unit radius, starts vibrating from rest and has initial deflection ur0 equal to fr. We have to find the deflection urt of the membrane at any instant t. Now the vibrations of a plane circular membrane are governed by two-dimensional wave equation using polar coordinates. As you know, its equation is given by utt equal to c square urr plus 1 by r ur plus 1 by r square u theta theta. Now for a radially symmetric, because circular membrane that we are considering is a radially symmetric membrane, so here u does not depend on theta, and therefore the above equation reduces to this term containing u theta theta will become 0, and we shall have utt equal to c square urr plus 1 by r ur. Now since the membrane is fixed, okay, since the membrane is fixed along the boundary r equal to 1, the radius of the membrane is given equal to 1. So the membrane is fixed along the boundary r equal to 1, and therefore the boundary condition is u1t equal to 0 for all t greater than or equal to 0. Now for solutions not depending on theta, because we have to find a solution which is not depending on theta, the initial deflection given is ur0 equal to fr. We are given ur0 equal to fr, and we are given that it starts initially at rest, it starts vibrating from rest. So we have initial velocity equal to 0, that is dou u over dou t at t equal to 0 is 0. Now using the let us apply the method of separation of variables. So using the method of separation of variables, let us assume that urt can be written as a function in r, that is wr, into a function in t, that is gt, and then we put it into the differential equation utt equal to c square urr plus 1 by r ur. So we put it in here, utt equal to c square times urr plus 1 by r ur. Now when you find partial derivative of u with respect to r, what you get is dw by dr into g, and when you find second order derivative you get d square w over dr square into g, and when you find partial derivative with respect to t, that is ut, what you get is w into dg by dt, and utt then will become w into d square g by dt square. So let us put these values here in this in the equation, this equation, okay, and then we divide the equation by w in g, okay. What we will get is a function, we will have the following. See, let me put it here. So c square utt equal to w into d square g over dt square, and the right hand side will be c square into urr. So c square into urr means d square w over dr square into g plus 1 by r dw ur is equal to dw by dr into g, okay. Now both sides we divide by wg, okay. When we divide by wg, what do you notice? This w will cancel, you will get d square g over dt square equal to c square times this g will cancel with this g, and this g we will have 1 by w d square w over dr square plus 1 by r dw by dr, okay. R we can write it as 1 by c square, here 1 by g is also there. So, we have c square by g into d square g by d t square equal to 1 by w d square w over dr square plus 1 by r dw by dr. Now, you can see left hand side is a function of t alone, this is a function of t only, while the right hand side is a function of r only. R and t are independent variables. So, they can be equal provided they are equal to a constant. Okay. So, let us take the constant to be k, then we have two situations. We are taking k equal to minus mu k equal to or you can say, let me take here instead of k you can take another constant, say mu. Okay. So, if you take mu equal to minus k square, mu equal to minus k square gives you these equations, d square w by dr square plus 1 by r dw by dr plus k square w equal to 0. The other equation is d square g by dt square plus c square k square gt equal to 0. Now, why we have taken minus k square mu equal to minus k square? Because if you take there can be three possibilities: mu is 0, mu is greater than 0 and then mu is less than 0. When if you take mu equal to 0, then d square g by dt square will give you gt equal to a t plus b, some constant a into t plus b. Okay. At t equal to 0 we have fr. Okay. U equal to fr, u equal to fr we are given, u r 0 equal to fr. So, fr will be equal to now you will have w u r t equal to w r into d 0. Okay. Now, w r is equal to a solution in r. Now, so this means g 0 must be 0, w r cannot be 0, otherwise f r will be 0. So, dr g 0 equal to 0 and g 0 equal to 0 means g 0 equal to f, so this means that f r equal to w r into g 0. So, g 0 must be some constant. Okay. So, this means that f r equal to some constant times w r. Okay. And then we have u 1 t equal to 0. So, u 1 t equal to 0 means f 1 we have u r t equal to w r into g t. Okay. So, when you put r equal to 1, what you get? u 1 t and u 1 t equal to 0, this is equal to w 1 into g t. Okay. So, here what do we get? G t cannot be 0, otherwise u will be 0. So, w 1 equal to 0. So, what we get is these situations mu equal to 0 and mu greater than 0, that is mu equal to some constant k square. They lead us to solutions which are not possible, which do where the boundary conditions that we are taking do not provide us solution. So, that provides us trivial solution. So, what we do is we take mu equal to minus k square, and when we take mu equal to minus k square, we get these two equations. So, putting s equal to k r in this equation, what we get is this equation 2 can be written as d square w over ds square plus 1 by s dw by ds plus w equal to 0. And this equation we know is a Bessel's equation. Actually, the Bessel's equation is of this form. Bessel's equation is x square d square y over dx square plus x times dy by dx plus n square minus n square x square minus n square, x square minus n square into y equal to 0, and n is greater than or equal to 0. N greater than or equal to 0 is a parameter. So, here what is happening is you take n equal to 0, then you get x square y double dash plus x y dash plus x square y equal to 0, or you get by double dash plus 1 over x by dash plus by equal to 0. So, this equation is of this form where we are taking n equal to 0, and that is why its general solution is w equal to C1 J naught s plus C2 by naught s, where J naught and by naught are Bessel functions of first and second kind of order 0. Now, we are given that the deflection in the membrane is always finite. Okay. So, by naught must become 0 because by naught becomes infinite as s approaches 0, and therefore, what we will have, C2 will be taken equal to 0. So, C2 becomes 0, and then what we have, W equal to C1 J naught s. Now, this W equal to C1 J naught s, the constant C1 will be absorbed while we write the general solution URT equal to WR into GT. So, this C1 will be absorbed in the constants which will come in GT part. So, we can take without any loss of generality C1 equal to 1. So, we have WR equal to J naught s. So, J naught s equal to J naught into J naught Kr, because we are taking s equal to Kr. Now, on the boundary of the membrane R is equal to 1, and so what we have, J naught K on the boundary of the membrane R equal to 1. So, J naught K equal to 0, because on the boundary we know that U1 T equal to 0. Okay. U1 T equal to 0 means U1 T is W1 into GT. Okay. U1 T is equal to now W1 into GT, and W1 is equal to J naught in K into GT. So, either J naught K is 0 or GT equal to 0. If GT equal to 0, then URT will be 0. So, trivial solution we will have, and therefore, we must take J naught K equal to 0, and J naught K equal to 0 means the zeros of the Bessel function of order 0. So, let the positive zeros of J naught s be denoted by s equal to alpha 1, alpha 2 and so on. So, then k is equal to alpha m, where m is equal to 1, 2, 3 and so on. Hence, the functions WMR is equal to J naught alpha m. For each value of the root of J naught s equal to 0, we will have a WR function. So, we write WMR equal to J naught alpha MR. They are the solutions of the equation 2, this equation which vanish at R equal to 1. Now, hence the general solution of the equation 1 satisfying the boundary conditions is, now this part d square g over dt square plus c square gt equal to 0 is here we have the auxiliary equation m square plus c square k square equal to 0. Okay, so m equal to plus minus I into ck. Okay, and so its general solution is of the type cos ckt, some constant into cos ckt plus some constant, say a times cos ckt plus b times sin ckt, and we write that as in this form. Okay, am cos c alpha mt bm sin c alpha mt into j naught alpha mr, because here k becomes alpha m, so we write it as cos c alpha mt, and the constants a and b which we take in the solution corresponding to this equation, equation number 3, okay, they will depend, they will change with each value of m. So, we write them as am and bm. Okay. So, now these UMRT are then the eigen functions of the problem, and the corresponding eigen values are C alpha m. Now, to find the solution which also satisfies the initial conditions, let us consider the series URT equal to sigma m equal to 1 to infinity am cos C alpha mt plus bm sin C alpha mt j naught alpha mr. M takes values from 1 to infinity. Now, here let us use the initial condition UR0 equal to FR. So, when you put t equal to 0, what do we get here? This part becomes am, this part becomes 0. So, we get sigma m equal to 1 to infinity am j naught alpha mr, and what we do is that this is putting t equal to 0, u r 0 equal to sigma m equal to 1 to infinity b am times j naught alpha m r. Then we multiply both sides with r times j naught alpha n r. And then integrate with respect to r over the interval 0 to 1. Okay, so u r 0 is given to be equal to f r. U r 0 is given to be f r. So let us put its value there, and we will get it as 0 to 1 r f r j naught alpha n r dr equal to summation m equal to 0 to infinity. Now am, here we have integral 0 to 1 r j naught alpha m r j naught alpha n r. We know that Bessel functions are orthogonal with respect to the weight function r. So j naught alpha m r j naught alpha n r they are orthogonal to each other with respect to the weight function r. So we have the value of this integral is 0 when m is not equal to n, and when m is equal to n we will have. So this is okay. So we write delta mn, okay, integral 0 to 1 r j naught we will put, let us put it like this, we have delta mn, okay, okay, let me write it as this is okay, 0 to 1 r j naught alpha m r j naught alpha n r dr is equal to delta mn, which is equal to 0 when m is not equal to n, okay, and which is equal to when it m is equal to n we will have 0 to 1 r j1 j naught alpha n square j naught square alpha n r. So that value will be 1 by 2 j1 square alpha n alpha n, okay. So this will be equal to, I can write it as okay, so 0 to 1 this is equal to delta mn. So what we will get, this will be equal to m is equal to n, so a n times 1 by 2 j1 square alpha n, okay. So we can get the value of a n, and thus a n is equal to, you see, a n is equal to 2 by j1 square alpha n integral 0 to 1 r f r into j naught alpha n r dr, okay. Now n is any integer from 1 to infinity, so we can replace n by m, and therefore am is equal to 2 by j1 square alpha m into integral 0 to 1 r f r j naught alpha m r dr in view of the orthogonal property of this integral 0 to 1 r j naught alpha m r j naught alpha n r which is equal to 0 when m is not equal to n, and 1 by 2 j1 square alpha n when m is equal to n. So now similarly using the partial derivative of u with respect to t at t equal to 0, what we get, Vm equal to 0. You see, we have now this, you differentiate this with respect to t, so we will have here am minus sine c alpha m into t, then c alpha m, and then Bm cos c alpha m into t into c alpha m, and j naught alpha m r. So then delta, when you differentiate this with respect to t and put t equal to 0, what we get, cos term will become sin, and so when we will put t equal to 0, this time this term will vanish, and here we will get sigma m equal to 1 to infinity bm cos c alpha m into t into c alpha m. So, cos c alpha m into t will become 1. So, bm c alpha m j naught alpha m r, and delta u by delta t, this is equal to 0 because we start with the vibrating with rest. So, this is equal to 0. So, this implies that bm equal to 0 for all m, and so we get u r t equal to sigma m equal to 1 to infinity am cos c alpha m t plus bm sin c alpha m, bm becomes 0. So, am cos c alpha m t into j naught alpha m r, where am is given by this expression. So, what we get is u r t equal to sigma m equal to 1 to infinity am cos c alpha m t j naught alpha m r, where am is given by 2 over j 1 square alpha m 0 to 1 r f r j naught alpha m r dr. So, we can omit this one. Let us go to this how we solve this problem. Let us go to Laplace equation in 3 dimensions. So, one of the most important partial differential equation in physics is the Laplace equation, del square u equal to 0, where del square u is the Laplacian of u. In Cartesian coordinates x y z in space, del square u is dy square u by dy x square dy 2u by dy by 2 dy 2u over dy z2. The theory of solutions of Laplace equation is called potential theory, and the solutions of this equation 1 that have continuous second order partial derivatives, they are called as harmonic functions. Now, this Laplace equation occurs in connection with a gravitational force. For instance, let us take a particle A of mass m which is fixed at a point x by z. So, let us say we have a point here x by z, and particle is fixed at this point whose mass is m. Okay, and another particle B is here of at the point x by z of mass small m. Okay, here we have mass to be capital M. So, then this point, the particle at A attracts the particle at B, okay, and the gravitational force is grad u, where u is gmm r over r. R is the distance between the point A and the point B. Okay. So, x minus x whole square plus y minus y whole square z minus z whole square, this function u of x by z. Okay. This function u of x by z is called the potential of the gravitational force and satisfies Laplace equation. We can show that del square u is equal to gm m is a constant. So, we have del square 1 by r, and del square 1 by r is equal to 0. So, in the case of a continuous distribution of mass, if a mass of density rho x by z be distributed throughout a region r in space, then the corresponding potential u x by z at an external point x by z is given by u x by z equal to k, the volume integral over the region r, and rho over r dx dy dz. Now, here we have r equal to under root x minus x whole square plus y minus y whole square z minus z whole square. Since del square 1 by r equal to 0 and rho is independent of x by z, we get del square u equal to k times the integral over the region r into rho del square 1 by r dx dy dz equal to 0. Now, this implies that the gravitational potential u given by 2 satisfies Laplace equation at any point which is not occupied by the matter. Laplace equation also occurs in electrostatics and incompressible fluid flow. If the temperature u is independent of time, that is we are in the steady state, then the heat equation ut equal to del square u reduces to the Laplace equation. Now, to determine the solution of Laplace equation satisfying the given boundary conditions on certain surfaces, it is desirable to represent the surfaces in a simple manner. For this, we need to transform the Laplacian del square u into other coordinate systems. So, let us look at the Laplace equation in cylindrical coordinates. The cylindrical coordinates we are taking as rho phi z. If you take any point x by z in space, drop the perpendicular from the point, let us say this is P, onto the xy plane, say this is P dash, join O to P dash, okay, draw through P dash lines parallel to x and y axis, okay. Then this angle is pi by 2, this angle is also pi by 2, and what we have, this is your rho, okay, OP dash is rho, and the angle that OP dash makes with x axis, this is phi, okay. Now this is x by z, so what we have, OX is equal to x, and OY, OX equal to x, OY equal to y, okay, and draw through P line parallel to this OP dash, so this is your OZ, okay. So then what happens, this is your OZ. Now what do we have, this is x, this is rho, so x equal to rho cos phi and y equal to rho sin phi and z equal to z. So the coordinates x, y, z are related to the cylindrical, these coordinates are called cylindrical coordinates, rho, phi, z, they are called as cylindrical coordinates, and they are related to the Cartesian coordinates x, y, z by the relations x equal to rho cos phi, y equal to rho sin phi, z equal to z. And so from here we can see x square plus y square is equal to rho square, okay. Now we have the del square u is equal to this is del square u in Cartesian coordinate, del square u equal to 0, and we have seen that when we change from Cartesian coordinates x y to the polar coordinates r theta, this uxx plus u by y becomes u r r plus 1 by r u r plus 1 by r square u theta theta. So instead of r theta, now here we have rho and phi, so we get this, for this part we get u rho rho plus 1 by rho u rho plus 1 by rho square u phi phi, okay, and z does not change, z remains the same, so we get u z z equal to 0. So this is cylindrical, this is Laplace equation in cylindrical polar coordinates. Now let us see how we solve this equation in cylindrical polar coordinates. Again by the method of separation of variables we will solve it. So we have to solve the equation, we can write this equation, you can see we can write this equation also as 1 over rho if I multiply the partial derivative of rho u rho with respect to rho and multiply by 1 over rho, then what do we get? This is equal to 1 over rho times derivative of rho with respect to rho is 1, so we get u rho, and then we get rho u rho rho, okay. So what we get here, u rho rho plus 1 by rho u rho. So u rho rho plus 1 by rho u rho, this part of the Laplace equation in cylindrical polar coordinates can also be expressed as 1 by rho del over del rho rho u rho, okay. So I can also write it as 1 by rho so this plus 1 by rho square u phi phi plus u z z equal to 0. This is another way of writing this equation, okay. So what we do is we have 1 by rho del over del rho u rho plus 1 by rho square u phi phi plus u z z equal to 0. Now let us consider a possible solution, r rho into h phi into z z, okay. R is a function of rho only, h is a function of phi only, z is a function of z only. When we substitute this solution u rho phi z into this equation and divide by r h z, then what do we get? Del square u by u is r h z. So we will get 1 by rho del over d over d rho d r over d rho over r plus 1 by rho square d square h by d phi square over h plus d square z by dz square over z equal to 0. Now what we can do, you can this term and this term, let us say this is term 1, okay, this is term 2, okay. So we can, if you write 1 plus 2 and this is 3, okay, equal to minus 3. Retain term 1, term 2 on the left, take term 3 to the right, okay, then you have the left side depends only on rho and phi. Left hand side is independent of z, okay. Right hand side depends on z only. Okay. Left hand side is a function of r and phi which are independent of z, and r and phi themselves are independent to each other. So each side will be equal to a constant. So 1 plus 2 equal to minus 3 minus 33 equal to some constant we have. Now let us take so this I have written, this is the first term, this is second term, equal to d square z over dz square upon z equal to let us put it equal to, this is minus here, minus d square z by dz square, we are dividing by r, h and z. So we get this equation, this is equal to some constant. Now let us take the constant to be equal to m square. When we take the constant to be m square, then take this constant is m square, and here we take 1 by h d square h over d phi square equal to m square, another constant. Then d square h over d phi square minus m square h gives you h phi equal to c1 m phi e to the power m phi plus e to the power minus m phi. Now in cylindrical coordinates the phi must be unique, so h phi plus 2 phi should be equal to h phi, but here if you replace phi by phi plus 2 phi, you do not get back h phi, and therefore this solution is not this solution is not appropriate for our problem. So we consider 1 by h d square h over d phi square to be equal to minus m square, and when we consider minus m square, we get h phi equal to a sin m phi plus b cos m phi. Now h phi plus 2 phi is equal to h phi, we can see from here, because h phi consists of trigonometric functions. Now for this h phi plus 2 phi to be equal to h phi, it is necessary that m be an integer. So for the condition h equal to phi, h phi plus 2 phi equal to h phi, we have to assume that m is an integer. Now consider 1 over z d square z by dz square equal to lambda square. So here what do we notice, d square z over dz square is minus kz, okay. Let us take it equal to k to be equal to minus lambda square. So when we take minus lambda square, z equal to a sin hyperbolic, because this is d square z over dz square minus lambda square into z equal to 0. So it is, its auxiliary equation is m square minus lambda square equal to 0, m equal to plus minus lambda. So it has two distinct real roots, and therefore we have z equal to some constant a times e to the power lambda z plus b times e to the power minus lambda z, and this can also be written in terms of sin hyperbolic cos hyperbolic functions. So we have a sin hyperbolic lambda z plus b cos hyperbolic lambda z. If you choose this k to be lambda square, then d square z over dz square will be equal to minus lambda square z. So if we choose minus lambda square, we get the solution as a sin lambda z plus b cos lambda z. Now corresponding to these two different solutions, we will have two different solutions of the given equation. Now here rho d upon d rho, rho dr over d rho, and then this is equal to now when we choose here this quantity, if we choose it to be a lambda square, okay, we have chosen this to be lambda square, okay. So this we choose as lambda square, and d square z over dz square upon z, if we choose lambda square, then we will get this one, yeah, lambda square rho square, and this is then lambda square rho square, because we had chosen it as m square, so lambda square rho square minus m square into r equal to 0. This is the case, this one. When we choose here this one 1 over z d square z over dz square, when we choose as lambda square, so we get this equation, and this is Bessel's equation, and where the solutions are r equal to c jm lambda rho d nm lambda rho, c and d are constants, jm and nm are Bessel functions and Newman functions of order m, and if you take 1 over z d square z over dz square to be minus lambda square, you get here minus lambda square rho square minus m square into r, whose solution is r equal to e times im lambda rho plus f times km lambda rho. E and f are constants, im lambda rho and km lambda rho are modified Bessel functions of order m. Now let us note the following, km lambda rho and nm lambda rho, this nm lambda rho, they diverge at r equal to 0. So if region of interest includes r equal to 0, then we must take this f this d equal to 0 respectively, while if r tends to infinity, then jm lambda rho and im lambda rho diverge. So in this case we must take c and d equal to 0, this c 0 and this this e 0, this e, okay, 0. So we have to see the problem and then decide whether the region includes r equal to 0. If the region includes r equal to 0, then and if it is appropriate to choose minus lambda square, you will have this solution. In this solution you will take km this f equal to 0. If you for your problem this is the solution, then you will have this solution. In this solution you will take d equal to 0, okay. So and if your region includes the case of r tending to infinity, then and your equation is this, you choose e equal to 0. If your equation is this, you choose c equal to 0. So this is how we do it. Now let us consider a hollow right circular cylinder of radius a, which has its axis as coincident with z axis, ends are at z equal to 0 and z equal to L. This is z equal to L, this is z equal to 0. The potential on the end surfaces is 0, potential on this face B equal to 0, potential on this face B equal to 0, and potential on the cylindrical surface is given as a constant B naught. On this curved surface, potential is given as B naught. Now we have to find the potential anywhere inside the cylinder. Now here in this solution we have taken potential as u, okay. So I have denoted it by u. So we have to solve the equation del square u by del rho square plus 1 by rho del u by rho del rho 1 by rho square del square u by del phi square del square u by del b z square equal to 0. The boundary conditions are now when z equal to 0, the boundary end faces are at 0 temperature 0 potential, okay. End faces this and this are at 0 potential. So u phi rho phi 0 is 0, u rho phi L is 0, and when rho is equal to a on the curved surface, potential is V naught, and when rho is equal to 0 here this one, oh okay, here at this point is r equal to 0. So here the potential is finite. Now let us consider u rho phi z equal to r rho h phi z z, then we have this equation. We know that 1 over h d square h by d phi square is equal to minus m square, because if you take plus m square you get e to the power m phi, and e to the power minus m phi, where we notice that when h phi plus 2 pi is not equal to h phi. So we have to consider minus m square, and there when you this consists of a cos m phi and plus b sin m phi. H will be equal to a cos m phi, b sin m phi. So h phi plus 2 phi will be equal to h phi plus 2 phi will be equal to h phi, provided m is an integer. So here for h phi plus 2 pi to be equal to h phi, m has to be taken an integer, and u rho phi z equal to 0 at z equal to 0 and z equal to L. Therefore 1 by z d square z over dz square will have to be taken minus k square, and that will plus k square will not do. So that will lead us to a trivial solution. So z equal to c cos sin kz plus d cos kz. Now r therefore must be a solution of this equation, because we have taken it as minus k square. So, we have minus k square here, and this is taken as minus m square. So, we get minus m square by rho square r. So, this is a Bessel's equation of order m, and its solution is r equal to E I m k rho plus f k m k rho. Now, u rho phi 0 equal to 0, at z equal to 0, u is 0. So, u is 0 means d must be 0, okay, and u rho phi l is 0, at z equal to l, u rho phi z is 0. So, we shall have sin k l equal to 0. Sin k l equal to 0 will give you k equal to n pi by l. N equal to 0 will lead us to a trivial solution when n is negative integer, because of sine function, sine minus theta is minus sine theta. So, minus sine will be absorbed in the constants, and therefore, we will take positive integral values of n. Now, u 0 phi z is equal to finite. So, u 0 finite equal to g is equal to finite means the region includes r equal to 0, and when region includes r equal to 0, we have to consider f equal to 0, this constant f equal to 0. So, f is 0, and therefore, u rho phi z becomes sigma n equal to 1 to infinity, m varies from 0 to infinity, I m n pi over l rho sin n pi over l z, a m n cos m phi plus b m n sin m phi. This m comes from h phi, and n comes from this this one, this equation, okay. From here we come get this n. So, there will be double summation. Now, we put here u a phi z equal to v naught. Let us use this equation. Put rho equal to a. When rho is equal to a, u a phi z is equal to b naught. So, b naught will be equal to this I m n pi l. Here we will have a, and this is what we will get. Now, multiply both sides by sin p pi over l z, and then integrate over 0 to l. So, we will have left side like this, right side will integral 0 to l sin n pi over l into z, sin p pi over l into z dz, and now this is this integral is l by 2, okay, when n is equal to p, and when n is not equal to p, this integral is 0. So, we will have the following: minus b naught cos p pi over l z, l over p pi, this is l by 2 this, and then minus b naught over p pi cos p pi is minus 1 to the power p. We have this equation, and this we have half l, we have cancelled both sides, this l with this, and we get this equation I m p pi over this one, okay. Now, r we can say sigma m equal to 0 to infinity I m p pi over l a m p cos m phi plus b m p sin m phi is equal to 4 b naught over p pi, where p is odd, 0 when p is even. Hence, if p is an odd integer, okay, we have sigma m equal to 0 to infinity I m p pi over l a m p cos m phi plus b m p sin m phi equal to 4 b naught over p pi. Now, left side contains cos m phi sin m phi terms, but right side does not contain cos m phi sin m phi terms. Therefore, m has to be taken 0. So, we have I naught p pi over l a 0 p 4 b naught over p pi, and this gives us the value of a 0 p. A 0 p equal to 4 b naught over p pi into 1 over I naught p pi over l a. P is an odd integer, and this leads us to the solution u rho phi z equal to 4 b naught over pi, where n runs over odd integral values into 1 by n sin n pi z over I naught n pi a over l into I naught n pi over l. So, this is an example on the cylindrical polar coordinates when we convert the Laplace equation into cylindrical polar coordinates. In the next lecture, we shall consider spherical polar coordinates, and will solve Laplace equation in spherical polar coordinates. Thank you very much for your attention.